Hello. In this presentation, I'll be giving a general overview of map projections and the components that make up a map projection. I'll start with an overview of projection surfaces, delve into coordinate grids, talk about datums, and talk about a few specific map projections. So, as a child, I learned that it was Columbus who discovered that the world was not flat, but they should have told me about Eratosthenes, the Greek scientist and father of geography who, before he died in 194 BC, was able to not only determine that the Earth was not flat, but also to measure the circumference of the Earth within a reasonable degree of accuracy. He also created maps of the Earth using his own map projections. Now, map projections are a way of representing the Earth, which is a three-dimensional object, on a two-dimensional plane. There is no way to do this without distortions, so cartographers have to choose the characteristic that will be shown accurately at the expense of the others, or perhaps how to present a compromise of several characteristics, things like area and shape, distance. So there really is no one best projection for mapping. There are countless projections out there for different purposes, and none of them are perfect. The most widely used map projection in the world, the one you likely use on your phone, was created way back in 1569 by a fellow called Gerard de Cremer, but you might know him by his Latinized name, Gerardus Mercator. Now, his goal was to create a map with just the right characteristics for navigation at sea. So to accomplish this, he had to accept some sacrifices with other characteristics, like area. To illustrate this, let's take a look at this Mercator puzzle. Now, which country would you guess this is? Now, how about if I drag it up here? Notice how large it becomes? Okay, so it's obviously Greenland, but on the Mercator map, areas closer to the equator are more accurate, but as you go away from the equator, areas are wildly distorted, giving most of us the idea that Greenland is almost as big as the continent of Africa, when in fact it's hardly larger than a few African nations. So Mercator's projection is a cylindrical projection. So what do we mean by cylindrical, and for that matter, what do I mean by projection? Well, we use the word projection because we are actually projecting the globe onto a flat surface. In a cylindrical projection, we project the globe onto a cylinder. Now imagine a light source in the middle of a globe which has a cylinder wrapped around it. The light projects the features of the globe onto the cylinder, which we can then unwrap to create our map. Now, a cylinder is not the only surface that we use. We could also use a plane or a cone, and together these are the three main projection surfaces. We could also play with different alignments of the globe and the projection plane. If we align the cylinder horizontally, we call that a transverse cylindrical projection. If we align it at an angle, we call it an oblique cylindrical projection. And with planes, if we put the center of a plane on one of the poles, it's called a polar azimuth, a polar azimuthal projection, azimuth meaning direction. If you angle that plane, it's called an oblique azimuthal. And with cones, projection using cones are called conical. And the cone is typically placed on the globe so that the point of the cone, or the apex, aligns with one of the poles. So the cylindrical projection produces straight meridians and straight parallels, which are perpendicular to one another, producing a very nice grid. The conical projection projects the meridians onto the cone as equidistant straight lines, radiating out from the apex. But the parallels are now circular arcs, which are centered on the apex. The angles between meridians are now shown smaller than their true angles. That's the conical projection. The azimuthal projection, the one using the plane, produces meridians as straight lines radiating out from a point, but they are spaced at their true angles instead of the smaller angles of the conic projections. The parallels of latitude are complete circles centered on the pole. So projecting the surface of the Earth onto a flat surface is just one aspect of producing a usable map. We also need a coordinate system. So we superimpose a network of latitude and longitude lines, these meridians and parallels, on the surface of the Earth. Most people are familiar with latitude and longitude. There are parallels of latitude, where the equator is 0 degrees, and meridians of longitude, where the prime meridian is an arbitrary choice. In 1541, Mercator drew a prime meridian for one of his maps precisely through a place called Fuerteventura in the Canary Islands, which is now what we would call about 14 degrees west. The prime meridian we use today is based on the meridian that runs through the Airy Transit Circle of the Royal Observatory in Greenwich, London, England. It was chosen by a man called George Biddle Airy in 1851 and became the international standard a few decades later. But you might notice that if you check the coordinates of that location on one of today's maps, you may find that the longitude is not exactly 0 degrees. So 51 degrees of latitude and 0 degrees longitude, 0 degrees 0 minutes, and 5.3 arc seconds west. So why? Why is that? Well, the World Geodetic System of 1984, or WGS-84 for short, defines a slightly different prime meridian. And this is the system that we use today. The meridian that they describe is one that's about 5.31 arc seconds, or 102.5 meters east of the Greenwich Meridian. That's about 336 feet east of the Greenwich Meridian at the latitude of the Royal Observatory. And this is known as the IERS Reference Meridian, which stands for International Earth Rotation and Reference Systems Service. So why did they change it? Why did IERS change the reference meridian? Did they want to mess with the British? No, not at all. With satellite technology, we can get very accurate measurements of the Earth's gravity. Satellites change the reference from the surface of the Earth to its center of mass, around which all satellites orbit, regardless of surface irregularities. The change in prime meridian was caused by the requirement that satellite-based geodetic reference systems be centered on the center of the mass of the Earth. And due to the shift of tectonic plates, the prime meridian slowly shifts as well. And that brings us to the heart of our map projection system. To really get an accurate projection, we have to start with an accurate 3D model of Earth. Now, we've established that the Earth isn't flat, but it's not exactly round either, and nor is it a perfect sphere. In fact, we've been able to get a better idea of the Earth's true shape over time, and it turns out that it's bumpy and lumpy and rather oddly shaped, and there's this uneven distribution of mass on our planet. And the greater the concentration of mass, the greater the gravitational pull. And every map projection system has to have some kind of model of Earth's shape. One part of that model is called the geoid. The geoid is basically the shape of Earth measured at mean sea level. And you get this by measuring the Earth's gravity signals, which undulate and can vary. They change day to day, even minute by minute. Now, the geoid is part of what we call a datum, which is a Latin word meaning given, as in this information is a given or a base of information. It's the same root as the word database. Datums are at the heart of our map projections because we use datums to translate positions indicated on maps, paper or digital maps, to their real position on Earth. Each datum contains also an ellipsoid, which is essentially a stretched sphere. It's also sometimes called an oblate spheroid, meaning a flat sphere, a sphere that's been flattened a bit at the poles due to Earth's rotation. So this ellipsoid is part of the datum as well. And the Earth is not really a perfect oblate spheroid. It's not really a perfect ellipsoid because mass is distributed unevenly within the planet, as we discussed with the geoid. But thinking of it this way as an ellipsoid makes the math easier while maintaining a reasonably accurate estimate. The ellipsoid is meant to be centered with the predicted center of Earth. Now, there are two main parameters for an ellipsoid, a radius at the equator and a flattening parameter. The World Geodetic System of 1984, WGS-84's datum surface is an ellipsoid with major radius of 6,378,137 meters at the equator and a flattening of 1/298.257 and some change. Now, the datum also contains one or more ground control points from surveyed locations on the Earth's surface. These establish reference points on the surface or on the ellipsoid using the coordinates we chose for our projection. So to summarize, our map projection or coordinate reference system, we chose a map projection type such as conical or cylindrical. Then we choose a network of meridians and parallels and coordinates for those, including a prime meridian, which are all based on our datum. And the datum includes a geoid, which is a gravitational model or mean sea level representation. The datum also includes the ellipsoid, that flattened sphere, and one or more ground control points defined by our preferred coordinates. Now back to WGS-84. WGS-84 is an Earth-centered, Earth-fixed terrestrial reference system and geodetic datum. It defines all of that stuff. It's based on a consistent set of constants and model parameters that describe the Earth's size, shape, and gravity, and its geomagnetic fields. That's the geoid and the ellipsoid. WGS-84 is the standard U.S. Department of Defense definition for a global reference system for geospatial information and is the reference system for the Global Positioning System, otherwise known as GPS. So you'll find a lot of map projection systems or coordinate reference systems based on WGS-84. There are newer, more accurate datums out there, systems out there such as the Earth Gravitational Model of 2008, EGM 2008, but WGS-84 has a margin of error of less than 2 centimeters, so it's certainly accurate enough to get you to the nearest Indian restaurant. And there are many older datums and systems as well, such as the North American datum of 1927, NAD-27, and also the North American datum of 1983, NAD-83, which uses the ellipsoid found in something called the Geodetic Reference System of 1980, GRS-80. Well, let's look at another popular coordinate reference system. It's called UTM, which stands for Universal Transverse Mercator. UTM's projection and grid were adopted by the U.S. Army in 1947 for designating rectangular coordinates on a large-scale military map of the entire world. You may have recognized the terms transverse and Mercator. Let's examine those terms, starting with Mercator. Now this tells us that the projection is based on Gerardus Mercator's projection. So it must be a cylindrical projection, meaning that the globe is being projected onto a cylinder. Transverse tells us that instead of placing the cylinder from the top to the bottom, so that the equator is touching the cylinder, it's placed on the side so that a meridian of the globe touches the cylinder rather than the equator. This is a key feature of this system and a good reason to use a transverse projection because scale is true along the meridian that touches the cylinder. UTM divides the Earth into 60 zones, each generally about 6 degrees wide in longitude. And because it's a transverse projection, each one of those zones will have true scale along its meridian. And with that in mind, it's not really just one projection, it's multiple projections, because each of those zones has its own projection. Each one of those zones is aligned with that cylinder. UTM uses the NAD-83 datum, which uses the GRS-80 ellipsoid. And hopefully, those terms mean something to you now. Well, that's all the time we have for now. And if you have any questions, please don't hesitate to get in touch with me. I'm Robert Parker, and I'm rparker@lizardtech.com. My email address is rparker@lizardtech.com. I hope you've enjoyed this presentation, and even more so that it has been helpful to you. Don't forget to like and subscribe to our channel, and thanks for watching.